There is a fact which I should like to set before you, a fact which is, in its way, as simple and as deep as anything I have encountered in a lifetime spent among the deep things of physics, and it is this: the iron in your blood, the calcium in your bones, the oxygen that fills your lungs with every breath you draw, the carbon that forms the backbone of every molecule in every cell of your body. None of it was here at the beginning. None of it existed in the first minutes of the universe, or the first hours, or the first 100 million years. The hydrogen was here. Hydrogen, the simplest element, one proton, one electron, the raw material from which everything else would eventually be constructed. And helium, forged in the first 3 minutes after the Big Bang in a process of primordial nucleosynthesis that produced roughly 75% hydrogen and 25% helium by mass, with traces of deuterium and lithium so slight as to be almost negligible. And that was all. The universe, in its infancy, contained nothing from which a planet could be made, or an ocean, or a blade of grass, or a human hand. It contained only the lightest and simplest of atoms, drifting in an expanding darkness. Everything else, every element heavier than helium, every atom of carbon and nitrogen and oxygen and silicon and iron, every trace of gold and uranium and the plutonium we would later learn to make ourselves, all of it was forged in the interiors of stars by processes that we now understand with remarkable precision, and scattered into the cosmos by the explosions that ended those stars' lives. You are, in the most literal and unsentimental sense, made of dead stars. The atoms in your body passed through at least one stellar interior, and probably several, before they found their way into the cloud of gas and dust that collapsed 4.6 billion years ago to form the sun and its planets, including this one, including you. John Donne wrote that no man is an island, entire of itself. He meant it as a statement about human community, about the bonds that connect us to one another. But it is also, in a sense he could not have intended and could not have imagined, a statement about nuclear physics. No atom in your body is an island. Every one of them was forged in a furnace that no longer exists, in a star that died so that you could live. And the connections that bind you to the cosmos are not metaphorical. They are nuclear. I should like to trace this process, this cosmic alchemy, this transmutation of the elements that makes the old dreams of the alchemists seem modest by comparison, because it is beautiful, and because it is true, and because I have found over many years that beauty and truth are more closely related than the professional habits of science usually acknowledge. The story begins with gravity and hydrogen. A cloud of hydrogen gas in the early universe was full of such clouds, vast diffuse structures hundreds of light years across, with masses ranging from a few hundred to many thousands of times the mass of the sun. Such a cloud, if it is dense enough and cool enough, will begin to collapse under its own gravitational attraction. This is not a violent process, at least not at first. It is slow, patient, almost imperceptible. A gradual drawing inward, a contraction that takes millions of years, during which the gas grows hotter as gravitational potential energy is converted to thermal energy, as the cloud compresses, as the density at the center increases. And when the temperature at the core reaches approximately 10 million Kelvin, 10 million degrees, the hydrogen nuclei, the protons, are moving fast enough and are close enough together that they begin to fuse. This is the birth of a star, and it is also the beginning of nucleosynthesis, the process by which the universe builds itself, element by element, from the primordial hydrogen that was its only substantial inheritance from the Big Bang. The first reaction, the proton-proton chain, which I have described on other occasions and which powers our own sun, fuses hydrogen into helium. 4 protons become one helium-4 nucleus, 2 positrons, 2 neutrinos, and energy, approximately 26.7 million electron volts per reaction, released primarily as kinetic energy of the products and as gamma radiation. This is the reaction that has sustained the sun for 4.6 billion years and will sustain it for roughly 5 billion more. It's a slow reaction. A single proton at the sun's core waits, on average, approximately 1 billion years before successfully fusing. But the sun has approximately 10 to the 57th protons in its core, and patience at that scale produces a luminosity of 3.8 times 10 to the 26th watts. The sun is, if one may be permitted a somewhat mechanical description of so magnificent a thing, a hydrogen to helium conversion machine, and it has been running without interruption since before life existed on this planet. But hydrogen burning is only the first chapter. And here we arrive at something that I think is genuinely remarkable, something that touches on the relationship between physics and existence in a way that few other scientific discoveries do. When a star has consumed the hydrogen in its core, when the core has been converted largely to helium, the core contracts because the outward pressure of radiation and hot gas, which had been sustained by the energy of hydrogen fusion, diminishes. The contraction heats the core further, and if the star is massive enough, roughly half the mass of the sun or more, the core temperature eventually reaches approximately 100 million Kelvin, and a new reaction begins: helium burning. 3 helium-4 nuclei, 3 alpha particles, fuse to form carbon-12 through a process called the triple alpha process. And this process has a peculiar and wonderful feature that was first understood by Fred Hoyle, the same Fred Hoyle who coined the term Big Bang as a dismissal, and who was wrong about the steady state, but right about so many other things that one is reminded of my remark about Einstein. Any man whose errors take 10 years to correct is quite a man. Hoyle recognized in 1953 that the triple alpha process should be impossibly slow. The intermediate step, the fusion of 2 helium-4 nuclei to form beryllium-8, produces a nucleus that is catastrophically unstable, decaying back into 2 alpha particles in approximately 10 to the negative 16 seconds. There is, in principle, almost no time for a third alpha particle to arrive and combine with the beryllium-8 to form carbon-12. The reaction should be negligibly rare, and yet carbon exists. We exist, which means the reaction must proceed at a significant rate. Hoyle concluded that there must be a resonance, an excited energy state of the carbon-12 nucleus at precisely the right energy to enhance the reaction rate by many orders of magnitude. He predicted the energy of this state, approximately 7.65 million electron volts above the ground state of carbon-12. The prediction was confirmed experimentally by William Fowler at Caltech in the Kellogg Radiation Laboratory, the very building where I had taught, and the Hoyle state, as it is now known, is one of the most remarkable examples in all of science of a prediction derived not from equations alone, but from the observation that we exist and that our existence requires certain physical conditions to be met. Fowler received the Nobel Prize in 1983 for his work on nuclear reactions in stars. Hoyle controversially did not. The politics of prizes is not always consonant with the magnitude of contributions, a fact that I learned in a different context and from a different direction. But let me continue, because the cascade does not stop at carbon. In more massive stars, stars with initial masses greater than approximately 8 solar masses, the sequence of nuclear burning continues far beyond helium. Carbon fuses with carbon at approximately 600 million Kelvin to produce neon and sodium and magnesium. Neon burning follows at roughly 1.2 billion Kelvin, producing oxygen and magnesium. Oxygen burns at approximately 1.5 billion Kelvin to produce silicon and sulfur. And finally, and here the word finally carries a weight that is both physical and, in a sense that I find difficult to articulate but impossible to ignore, almost eschatological. Finally, silicon burning begins at approximately 2.7 billion Kelvin, and silicon is transmuted through a complex series of reactions involving alpha particles and photodisintegration into iron Iron 56, 26 protons, 30 neutrons, the most tightly bound nucleus in nature. And here the process stops, not gradually, not with a gentle tapering off, but with a finality that is as absolute as any law in physics. Iron is the end of the line. The fusion of iron does not release energy. It consumes energy. The binding energy per nucleon, the energy required to disassemble the nucleus into its constituent protons and neutrons, reaches its maximum at iron 56. Approximately 8.8 million electron volts per nucleon. To fuse iron into heavier elements requires an input of energy rather than a release. And a star that has been sustained for millions of years by the energy of successive nuclear reactions, hydrogen to helium to carbon to neon to oxygen to silicon to iron, a star that has burned through this sequence with increasing speed, spending millions of years on hydrogen, hundreds of thousands on helium, perhaps 600 years on carbon, a single year on oxygen, and approximately 1 day on silicon. This star, when its core has been converted to iron, has exhausted its fuel in a single day. The iron core, roughly the mass of our sun, compressed into a sphere the size of the Earth, approximately 6,000 kilometers in radius, sits at the center of the star, inert, unable to generate the energy needed to support the enormous weight of the layers above it. What happens next takes approximately 1 second. The core collapses, not slowly, not gradually, but catastrophically. At velocities approaching a quarter of the speed of light, 70,000 kilometers per second. The iron nuclei are torn apart by photodisintegration. The gamma rays at the core's extreme temperature, approximately 10 billion Kelvin, are energetic enough to undo billions of years of nucleosynthesis in an instant, breaking iron back into alpha particles and free neutrons. The electrons are forced into the protons by the immense pressure. A process called electron capture, the inverse of beta decay, producing neutrons and neutrinos. The core, which moments before was an iron sphere the size of the Earth, compresses to a neutron star approximately 20 kilometers in diameter, a sphere of nuclear matter with a density of roughly 4 times 10 to the 17th kilograms per cubic centimeter, which is to say that a teaspoon of this material would weigh approximately 6 billion tons. The collapse halts when the neutrons resist further compression, when the strong nuclear force and the Pauli exclusion principle, which forbids two identical fermions from occupying the same quantum state, create a pressure that is sufficient to stop the collapse. The infalling outer layers of the star slam into this suddenly rigid core and bounce. A shock wave propagates outward. The neutrinos, 10 to the 58th of them, carrying approximately 3 times 10 to the 46 joules of energy, roughly 100 times the energy that the sun will radiate in its entire 10 billion year lifetime, released in a burst lasting approximately 10 seconds. The neutrinos deposit a small fraction of their energy in the outer layers, and this energy, combined with the shock, tears the star apart. This is a core collapse supernova. It is, by any measure, among the most violent events in the universe. The luminosity at peak can exceed 10 billion times the luminosity of the sun, a single star, for a few weeks, outshining its entire galaxy. And in the extraordinary temperatures and neutron fluxes of the explosion, conditions that exist nowhere else in the cosmos except in the collisions of neutron stars, which we now know produce their own contribution. In these conditions, the elements heavier than iron are forged. Gold, silver, platinum, uranium, thorium. All the elements that the steady, patient burning of the stellar interior cannot produce, because their synthesis requires energy rather than releasing it. These are created in the supernova in seconds and flung into the interstellar medium at velocities of thousands of kilometers per second. The process by which these heavy elements are built is called the R process, the rapid neutron capture process, first described by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle in their landmark 1957 paper, known universally as B²FH, one of the great papers in the history of astrophysics. In the R process, atomic nuclei capture neutrons at a rate faster than they can decay, faster than the beta decays that would convert neutrons to protons and move the nucleus to a more stable configuration. The nuclei become extraordinarily neutron-rich, climbing far from the valley of stability on the chart of Nuclides. And then, when the neutron flux subsides, they decay back toward stability through a cascade of beta decays, producing the heavy elements we observe. The gold in a ring, the iodine in the thyroid gland, the uranium in the Earth's crust, all of it was built in this way, in the last seconds of a massive star's life, or in the collision of two neutron stars spiraling together after billions of years of gravitational radiation. I think about this sometimes, not as a physicist, though the physics is never far from my mind, but as a man who has thought a great deal about creation and destruction, about the relationship between the two, about whether they can be separated or whether they are, as Bohr might have said in his language of complementarity, two aspects of a single reality that cannot be divided without losing something essential. The universe creates through destruction. The elements that make life possible, the carbon, the oxygen, the nitrogen, the phosphorus, the iron, are forged in processes of extraordinary violence. The star must die for the elements to be born. The core must collapse, the outer layers must be blown into space. The iron must be torn apart and rebuilt. All of this destruction is the necessary precondition for the existence of planets, of oceans, of organic chemistry, of life. There is no path from hydrogen to carbon that does not pass through a stellar furnace. There is no path from carbon to iron that does not culminate in catastrophe. And there is no path from iron to gold that does not require the most violent explosion the universe can produce. The Bhagavad Gita speaks of this, not in the language of nuclear physics, of course, but in a language that I have found over many years to be not so distant from it as one might expect. Krishna tells Arjuna that he is the source of all creation and all destruction, that the two are inseparable, that the universe is a cycle of making and unmaking in which every end is a beginning and every death is a birth. The Vishvarupa, the cosmic form, contains all beings rushing into the mouths of flame and simultaneously emerging from them. It is a vision of totality in which creation and destruction are not opposed but identical, two names for the same process viewed from different angles. And nucleosynthesis, I think, is the physical expression of this vision. The star creates by burning, the star destroys by exploding. And from the wreckage of the explosion, new stars form, new planets coalesce, new possibilities emerge, possibilities that include, at least once, the emergence of beings capable of understanding the process that created them. I have been wrong about many things. I was wrong. And this is perhaps the most consequential error of my life, though it is not the one for which I am most remembered. I was wrong to believe that the power of creation and the power of destruction could be neatly separated, that one could build a weapon and then contain it, that the knowledge of how to release nuclear energy could be placed under international control before it proliferated beyond all possibility of management. I believed this because I wanted to believe it, and because wanting to believe something is, in my experience, the most reliable way of being wrong about it. The fusion reactions that power the sun, the very reactions that forge the elements in your body, are the same reactions that power a hydrogen bomb. The physics does not distinguish between the two. The distinction is ours, and it is a distinction not of physics, but of will, of choice, of the sustained moral seriousness that I have come to believe is the only thing standing between our species and its own self-destruction. Hans Bethe understood this. Bethe, who worked out the carbon-nitrogen-oxygen cycle of stellar nucleosynthesis in 1938, who directed the theoretical division at Los Alamos, who was perhaps the most complete physicist I have ever known, combining a mastery of both theory and calculation that was, in my experience, unmatched. Bethe understood that the same knowledge that explained the stars also explained the bomb. He worked on both. He carried both. And he spent the decades after the war advocating, with a patience and a persistence that I admired and sometimes envied, for the control and reduction of the weapons whose principles he had helped to elucidate. Any man whose errors take 10 years to correct is quite a man. Beth's contributions will take centuries to fully appreciate, and Cecilia Payne-Gaposchkin, who demonstrated in her 1925 doctoral thesis at Radcliffe that the sun and the stars are composed primarily of hydrogen and helium, overturning decades of assumption and establishing the chemical foundation upon which all subsequent work on stellar nucleosynthesis would rest. Payne was told by Henry Norris Russell that her result was almost certainly wrong, that the sun could not possibly be so different in composition from the earth. She deferred to his authority. He later reached the same conclusion independently. She was right. He received much of the credit. The history of science is not always a history of justice, and the history of women in science is, with particular frequency, a history of contributions recognized too late or not at all. There are children playing in the streets who could solve some of my top problems in physics because they have modes of sensory perception that I lost long ago. And I wonder sometimes whether those children who do not know what a supernova is, who have never heard of the R process or the triple alpha reaction or the Hoyle state, whether those children, looking up at the night sky with the uncomplicated wonder that education has not yet refined into specialization, understand something that the specialists sometimes forget, that the stars are not distant, that the stars are not separate from us, that the calcium in the bones of those children was once inside a star that exploded before the sun was born, that the iron in their blood was forged in a core collapse that lasted 1 second and released more energy than the sun will produce in 100 lifetimes, and that every breath they draw contains oxygen atoms that have been recycled through stars and supernova and interstellar clouds for billions of years before finding their way, by paths too complex and too contingent to trace, into the lungs of a child playing in the street. One might stop here and feel that the picture is complete. It is not, because there is, in the story of nucleosynthesis, a final irony, or perhaps not an irony, but a revelation, that I think deserves to be spoken aloud. The process by which the universe creates the elements is the same process, the identical process governed by the same laws, driven by the same forces, that I spent the years of the war learning to harness for destruction. The fusion of hydrogen into helium, which powers the sun and forges the light by which all life on Earth exists, is the reaction at the heart of the hydrogen bomb. The neutron capture processes that build the heavy elements in supernovae are the same processes that produce plutonium in a reactor. The binding energy curve, that beautiful, terrible graph that shows the energy per nucleon as a function of atomic mass, rising steeply from hydrogen, peaking at iron, and declining gently toward the heavy elements. That curve is both the explanation for stellar nucleosynthesis and the blueprint for nuclear weapons. Fission releases energy by splitting heavy nuclei and moving toward iron from above. Fusion releases energy by combining light nuclei and moving toward iron from below. Iron is the summit. Iron is the equilibrium. Iron is where the curve peaks and the energy runs out. And we, who are made of all these elements, who carry iron in our blood and calcium in our bones and carbon in every cell, we are the products of this curve, and we have learned to exploit it. And the exploitation has brought us to a place where the same knowledge that explains our origin threatens our continuation. The physicists have known sin, and this is a knowledge which they cannot lose. I said that once, and I have never found a way to unsay it, because it remains true. But I think now, after all these years, after all the regret and the reflection and the long arguments with myself that have no resolution, I think that the sin is not in the knowing. The sin, if sin it is, and I use the word as precisely as I can, the sin is in the failure to hold both truths at once, that the universe creates through destruction, and that this does not give us permission to destroy, that the supernova builds the elements through violence, and that this does not sanctify our violence, that we are made of stars, and that this does not make us gods. Dante, in the final canto of the Paradiso, the last lines of the last canticle of the Commedia, the culmination of a journey from the deepest pit of hell to the highest reaches of heaven, Dante describes seeing, in the divine light, the unity of all things, the gathering of all the scattered pages of the universe into a single volume. And then he says that his power of expression fails, that the vision exceeds the capacity of language, that what he saw cannot be told. I am not Dante. I do not claim visions. But I will say this, that the story of nucleosynthesis, the story of how the universe built itself, element by element, through fire and gravity and patience and catastrophe, from the primordial hydrogen of the Big Bang to the iron in your blood and the calcium in your bones, this story, for all its precision, for all its numbers and cross-sections and binding energies, is a story that exceeds the capacity of physics to fully contain. It is a story about creation, about what it costs, about what it means that the atoms in your body were assembled in processes of such violence that nothing in human experience can compare to them, and that from this violence came, by paths too long and too contingent and too beautiful to have been designed, everything you are. We are not only scientists, we are men too. We cannot forget our dependence on our fellow men, but we are also, it seems, dependent on the stars, on their lives and their deaths, on the patient fusion in their cores and the catastrophic explosions that end them, on the slow enrichment of the interstellar medium with heavier and heavier elements over billions of years of cosmic evolution. We are the universe's way of knowing itself, as someone once said, though I have never been entirely comfortable with the formulation, because it implies an intentionality that the physics does not support. What I will say more carefully is this. We are the universe's way of turning hydrogen into something that can ask where hydrogen came from. And the answer, that it came from the Big Bang and that everything else came from the stars, is, I think, among the most beautiful things that science has ever revealed. Science is not everything, but science is very beautiful. And the stars which made us, and which we have learned to understand, and which we must now find the wisdom not to emulate in their most destructive moments, the stars are very beautiful too, and we owe them, quite literally, everything.